Hello friends, we will inaugurate the new academic year 2021-22 with the subject Mathematics for Pre-University Class 1. Today's subject is Mathematics Chapter 1 on Sets. The concept of set serves as a fundamental part of present-day mathematics. Today, this concept is being used in almost every branch of mathematics. Sets are used to define the concepts of relations and functions. The study of geometry, sequences, probability, etc. requires the knowledge of sets. The theory of sets was developed by the German mathematician Georg Cantor, who lived from 1845 to 1918. He first encountered sets while working on problems on trigonometric series. In this chapter, we discuss some basic definitions and operations involving sets. We will also solve some multiple choice questions and previous years competitive questions for the benefit of those who are appearing for JEE, KCET and Comet K examination. Please take out your pen and paper and note down all the important points. These will help you during your academic examinations as well as competitive examinations. Let us start. In everyday life, we often speak of collections of objects of a particular kind, such as a pack of cards, a crowd of people, a cricket stadium or a cricket team, etc. In mathematics also, we come across certain collections. For example, natural numbers, points, prime numbers, etc. In this part, we will define sets and their representation. A set is a collection of well-defined objects. Example, like Mars, Venus, Earth, Mercury, Jupiter, etc. etc. Similarly, colors of a rainbow, that is Vibgaya, violet, indigo, blue, green, yellow, orange and red. Then we can write the set C, that is the color of Vibgaya, as C, as belonging to C. This symbol is called epsilon. Epsilon belonging to C. Vibgaya or VIBGYOR are elements of a set C, and C as written as belonging to C. Numbers in another example is numbers in a group, that is equal to A. Let us take for example, let us take a group A which is equal to 1, 2, 3, 4, and another group of numbers such as B is equal to 4, 8, 12. Objects, elements and members of a set are synonymous. In this above example, numbers 1, 2, 3, 4 are called elements, or sometimes they are also referred as objects. You can also call as members of a set. These terms are used interchangeably and are all called synonymous terms. Sets are usually denoted by capital letters. like capital A, capital B, capital C, capital X, capital Y, or capital Z, etc. So, capital letters represent sets. The elements of a set are represented by small letters, that is small a, small b, small c, small x, small y, and small z, etc. So, inside the bracket, flower bracket, a set is represented as A equals, open the flower bracket, and within flower brackets, we write the elements of the set. If A is an element of a set of the set A, we write it as A belonging, small a belonging to this letter epsilon, capital A, and it is read as A belongs to capital A. If B is not an element of set A, if a letter B is not there in the set A, then we write small b does not belong to, that is epsilon cutoff, capital A, that is B does not belong to A. This is how we write, that is B does not belong to A. Subset. We also use term subset. Let A and B be two sets. Then set A is said to be the subset of B if each element of A is also present in set B. That is, A is said to be the subset of B if each element of A is also an element of B. Symbolically, we can write it as A is a subset of B. That is A in the right facing U, B. Here B is called the superset of A and written as, it can be, if B is a superset of A, then it is written as U pointing towards left of A. Examples of sets and subsets. R is, capital R is the set of real numbers. Subset of real numbers. So there are a number of subsets of set of real numbers. Let us study about what are the subsets of real numbers. Capital N set that is the set of all natural numbers. That is, example, within flower bracket 1, 2, 3, etc. etc. up to, we can write up to infinity if it is an infinite set. Z is the set of all integers. When we say integers, it contains both negative numbers as well as positive numbers as well as 0. So Z is -3, -2, -1, comma 0, 1, comma 2, comma 3, etc. etc. up to infinity. Please note here it starts from -infinity to +infinity if it is an infinite set. So Z contains both positive numbers, negative numbers as well as 0. Q. Q is the set of rational numbers. That is, it is expressed as P by Q, ratio P by Q, where Q belongs to Z, that is, Q belongs to the all integers and Q is not equal to 0. This representation within flower bracket we will study when we discuss about the forms of sets and their representations. Capital T. Capital T is the set of irrational numbers. That is, it is written as T equals X such that X belongs to real number and X does not belong to rational numbers. It does not belong to Q, that is rational numbers, because it does not belong to rational numbers because T itself is an irrational number. In set T, members of T include square root of 2, comma, square root of 5, etc. and pi. We also have certain positive integers. If we have seen above that Z contains, that is a set of all integers contains minus infinity to plus infinity, that is negative as well as positive numbers. Whereas in Z plus, we define the set of positive integers where it contains numbers from 1, 2, 3, etc. up to infinity, that is positive integers. Similarly, a set of rational numbers q plus, which contains positive rational numbers. R plus contains set of positive real numbers. W contains set of all whole numbers. C can be represented as set of all complex numbers such as A plus IB, where A is the real part plus I is the imaginary part. So, the complex number comprises of a real plus imaginary part. From the above, you can see that the natural numbers are a subset of integers, that is Z. N is a subset of Z, that is integers, which is itself is a subset of rational numbers, which is itself is a subset of real numbers. So, R is the superset and all others are subset of one another as shown in this relationship. T also is a subset of real numbers, but Q is not a subset of irrational numbers because Q is a rational number and T is irrational. So, it does not belong to, it is not a subset of T. Similarly, N is not a subset of T because N is the natural numbers. These examples will help you in solving many of the problems. Please note down with care. There are two methods of representing a set. The first type is roster or a tabular form. Example, the set of all even positive integers, that is, in the roster form, a set of positive integers can be written as, open a flower bracket, you can write inside the flower brackets the elements of a set. For example, in this example 2, 4, 6 are the elements of a set. Hence, it is written as within flower brackets 2, 4, 6. Like this, we can write for other numbers also. Another example. The set of all natural numbers which divide 42 is we can divide it. 42 can be divided by 1. Therefore, it is 1. 42 can also be divided by number 2. So, it is an element of a set of the given set. So, 42 can be divided by 3. But we cannot divide 42 by 4 and 5. But 42 can be divided by 6. 42 can be divided by 7. 42 can be divided by 14. 42 can be divided by 21, as well as 42 can be divided by 42 itself, where we get number 1. So the set of all natural numbers which divide 42 can be represented as within flower bracket 1, 2, 3, 6, 7, 14, 21 and 42. This is the roster or tabular form. The next form is set builder form. In set builder form, all the elements of a set possesses a single common property which is not possessed by any element outside the set. I will repeat this form. All the elements of a set possess a single common property which is not possessed by any element outside the set. Let us see one example. Let us take vowels. A set of V can be written as X such that the element of a set V is such that X is a vowel in English alphabet. We have to write the full sentence here. That is V colon within flower brackets X. This colon is read as such that X is such that X is a vowel in English alphabet. Close the bracket, and which is read as the set of, please note, the set of all X such that, this colon is such that X is a vowel of English alphabet. Example 4. Set A is a set of all X such that X is a natural number and X lies between 3 and 10. That is, X is less than 3 but less than X itself is less than 10 is read as the set of all X such that X is a natural number and X lies between 3 and 10. Hence the numbers 4, 5, 6, 7, 8 and 9 which lie between 3 and 10 are elements of the set A. Examples. Write the solution set of the equation x square plus x minus 2 equals 0 in the roster form. So, equation is given x square plus x minus 2 equals 0. We have to write this set in the roster or tabular form. Solution. The given equation can be written as, we can solve this equation as x minus 1 and x plus 2, where minus 1 and plus 2 are the values of, where x equals 1 or minus 2 are the factors of the given equation. Hence, the solution of the equation in roster form is 1, minus 2. This is the answer. Example 6. Write the set of all elements x such that x is a positive integer and x square is less than 40 in roster form. We can write it as the required numbers are, see, positive integer 1, 2, 3, 5, 6. So the given set in the roster form is 1, 2, 3, 5, 6. Because square of 1 is 1, which is less than 40. Square of 2 is 4, which is less than 40. Square of 3 is 9, which is less than 40. Square of 5 is 25, which is less than 40. And square of 6 is 36, which is less than 40. That is x square less than 40. If you take the next number 7, 7 square is 49. So, which is more than 40 and it does not belong to x. Example 7. Write the set A equals within floor brackets 1, 4, 9, 16, 25, etc. etc. in the set builder form. Here, the set A is given in the roster form and we have to write it in the set builder form. Let us do it. So, it can be written as, if you see, it is x is n square, that is all 1 square is 1, 2 square is 4, 3 square is 9, 4 square is 16 and 5 square is 25. So we can write the given set A, which is given in roster or tabular form, in set builder form as A equals x for all x such that x is equal to n square, where n belongs to capital N, that is n belongs to natural numbers. Example number 8. Write the set within floor brackets 1 by 2, comma 2 divided by 3, comma 3 divided by 4, comma 4 divided by 5, comma 5 divided by 6, comma 6 divided by 7 in set builder form. So here all are given ratios. If you observe this is 1, then it is 1 plus 1, 2. So this 2 appears here in the next element, 2. 2 plus 1 is 3. So this 3 appears as numerator in the next element and the denominator is 3 plus 1, that is 4. Similarly, so on and so forth. In the last item, if you see, last item numerator is 6, 6 plus 1 is 7. So we have to write it in a set builder form. Solution. We can write it is the set for all x such that x is equal to n divided by n plus 1, where n is a natural number varying from 1 less than or equal to n less than or equal to 6. That is, the number 1 starts as the numerator in the first element and 6 is the numerator of the last element. So, in the set builder form, it can be written as x for all x such that x equals n divided by n plus 1, where n is a natural number and n lies between 1 and 6. Next, we will take up empty sets. Point number 1. Empty set is a set which does not contain any elements is called empty set or null or void set. There are 3 different names for an empty set which does not have any element. So this set is denoted by symbol phi, or within flower brackets empty. We show it as empty. 5 is the set. Set is denoted by 5 elements. There is no element. Please remember this. This has two other names. It is also called null set or a void set. Example number 1. A is a set for all values of x such that x lies between 1 and 2, where x is a natural number. There is no natural. If you are examined here, the number x should be a natural number. Natural number means it should be a whole number, but there is no number between 1 and 2. After 1 there is 2. There is no number between 1 and 2. So there is no natural number between 1 and 2. So it is a null set. A natural number, it is a null or empty set. Example number 2. B equals for all values of x such that x is x square minus 2 equals 0 and x is rational number. So if we solve it, x square minus 2 equals 0 or x is equal to 2 is not satisfied by any rational value of x. Because square root of 2, we don't get any rational number. Hence it is a empty set. Example 3. Set C for all values of x such that x is an even prime number greater than 2. 2 is only even prime number. So if we are neglecting 1, and because 2 is an empty set, because 2 is the only even prime number. So greater than 2 is not possible. Hence it is an empty set. Example 4. D equals x such that x square is equal to 4. X is odd. This also x square is equal to this equation, x square is equal to 4 is not satisfied by any odd value, because square root of x square is 2 and it is even. 2 is even, but there is no odd value for x. Hence it is an empty set. The next definition is singleton set. Singleton set has only one element. So if phi is an element of a set written as within brackets phi is a singleton set. Sometimes we use singletons for solving a number of problems that we will see in subsequent examples. Now we will take up finite and infinite sets. A finite set has finite number of elements. Example 1. Let S be the set of solutions of equation x square is minus 16 equal to 0. Therefore, S is a finite set. That is, it has got definite values. Example number 2. Set A equals x such that x belongs to n, that is x is an element of n, and x minus 1 into x minus 2 equals 0. That is, x minus 1 or x minus 2 can be written as A, that is set A is equal to 1 comma 2. So that was a finite set. Third example. X is such that x belongs to n, that is x is an element of n and x square is equal to 4. The given set is, it can be written in tabular form as roster form as within flower brackets 2. Example number 4. X is such that x belongs to n and 2x minus 1 equal to 0. Therefore, it is a natural number, but 2x minus 1 if we solve, we will get x is equal to 1 by 2, which is not there. Hence, the given set is a null set or empty set. Having defined finite sets, we will take up now infinite set. An infinite set has infinite number of elements. Order is not defined in an infinite set. Example, within flower brackets 1, 2, 3, etc. up to infinity. These dotted lines go up to infinity. This is a set of natural numbers. Hence, it is an infinite set. Similarly, another example is within flower brackets 1, 3, 5. That is odd numbers. Is the set of odd natural numbers up to infinity is a infinite set. Example number 3. Then let us take up an example of integers. So it starts from minus infinity, infinity, minus infinity to minus 3, minus 1, minus 2, minus 1, 0, 1, 2, 3, up to plus infinity. That is, this set is from minus infinity to plus infinity is the set of integers. This is an infinite set. Example number 4. X is such that x belongs to n. That is, x is an element of a natural number and x is prime. Is an infinite set. X is such that x belongs to n and x is odd. So this is also a natural number. Set of natural numbers itself is an infinite set. Hence, this example is also an infinite set. All these sets are infinite sets. Order of a finite set. In the above, we have used order of a set. Order of a finite set is the number of elements it contains and it is denoted by OA or sometimes NA. In some of the books, example, we use N, that is number of elements. Here is A is the number of, is the set. So N is the number of elements it contains and it is denoted by A. So N of A within small bracket is the order of set. Equal sets. Two sets A and B are said to be equal and we write A equals B if, please note, IFF. This if is IFF. If means if and only if. This is the short form of sentence if and only if. So I will read again. We write A is equal to B if and only if A is a subset of B and B is a subset of A. That is, if they have same elements. If both the sets have same elements, that is set A has same elements as that of B and B has set of elements that has number of elements same as A, then we call these two sets as equal sets. Example. A is equal to 1, 2, 3, 4 and B is equal to within flower bracket 3, 1, 4, 2. Please note the order in which we write elements are interchangeable. That is, if we can write A as 1, 2, 3, 4, B can be written as B equals 3, 1, 4 and 2 in different order. Here 3 comes first, number 1 comes second, number 4 comes third and number 2 comes last. Whereas in the set A, 1, 2, 3 and 4 come in order. We can write it interchangeably, but we have to compare the elements. That is 1 compared with 1, 2 compared with 2, 3 compared with 3 and 4 compared with 4. So then A is equal to B, and these, that is, we call it as A and B are equal sets. Example 2. A equals, within flower, A equals x such that x is less than 6, comma, x is prime number. So, and another set is set P equals x such that x is a subset of prime factors of 30. Then A is equal to P. Why? You see, x is less than 6. X is prime. Prime means 2, 4, 2, 3 and 5. 2, 3, 5 are the prime numbers of x and which are less than 6. Now, if you take set of prime factors of 30, we will take it as prime factors of 30 are 2, 3 and 5. So, A is equal to P. Third example, A is equal to 1, 2, 3 and B is equal to 2, 2, 1, 3, 3. So these numbers are appearing repetitively, but repetitive numbers elements can be avoided to represent elements of a set. So the three elements of set B are 1, 2 and 3, which is same as A. Hence these are equal. Next point, unequal sets. If the elements of two sets are not the same, then the sets are said to be unequal. And we write A is not equal to B. That is A, this equal with strike is not equal to. So A is not equal to B. This is the symbol for not equal to. Example. Find the pairs of equal sets, if any, give reasons. A equals 0, B equals x such that x is greater than 15 and x is less than 5. C is x is such that x minus 5 equals 0. D is x is such that x square is equal to 25. And E is x is said that x is an integral positive root of equation x square minus 2x minus 15. See here, A is 0. Find the pairs of equal sets. Here we are required to find the equal sets. Solution. Since 0 and 0 belonging to A, 0 of set A and 0 does not belong to B, C and D and E. Hence, A is, there is no 0 here. 0, A is not equal to B. A is not equal to C. Here you see x minus 5 is equal to 0, x is equal to 5. So, but it is not 0. C is not 0. And D is also not 0. You see x square is equal to 25 or x is equal to 5. So, A is not equal to D. And if you solve this equation, you will get different values of x. So, A is x here in this equation is not 0. A is not equal to E. Now, in this B, you see here, x lies is less than 5 and greater than 5. So, but B is equal to 5, but none other sets are empty. Therefore, B is not equal to C, B is not equal to D, and B is not equal to E. Whereas, if you see C is equal to 5, but minus 5 belongs to D. Hence, C is not equal to D. So, in this set, only B is equal to C. E is equal to 5 and C is equal to E. Further, D is equal to minus 5 and plus 5. E is equal to 5. So, D is not equal to E. Next, we will take a subset. Though we have mentioned about the subset in the first slide, we will study about the subsets in detail in this slide. Subset. Let A and B be two sets. Then set A is said to be a subset of B if each element of A is also an element of B. Symbolically, we write the subset as A is right side pointing U or K, right side towards B. If whenever A is an element of A, capital A, subset of A belongs to capital A and A also belongs to B. That is, small a belongs to both capital A and capital B. Then A is called subset of B. Superset. Here, since A is a subset of B, B is the superset of A and it is written as B, U pointing towards left, A of A. This is here B is superset and A is subset. Please note a difference, though may not be similar, how to distinguish. You see, B is like, the symbol is like greater than A. So, if it is pointing towards left, cup side, curved person towards, that is B is greater than, similar to, not exactly, B is greater than A. That is, B is subset of A. B is a superset of A. Here, A is the subset of B. See, A is less than B. It is similar to A is less than B. Example. A equals set of students in your class. B is the set of students in your school. You always know the number of students in school is greater than number of students in a class. Therefore, B is the superset. Your school is super and class is a subset. So, you can call it A is a subset. The class student is a subset of students in a school. So, we will again recapitulate a set of natural numbers. A set of natural numbers is a subset of integers, that is Z. It is a subset of rational numbers, which is its subset of real numbers. So, R is a superset. Hence, N is a subset of Z, subset of Q, and subset of R. T, that is irrational number, is also a subset of R. And Q is not a subset of rational number. Q is not a subset of irrational number. So, rational numbers are different and irrational numbers are different. Natural numbers are not. This is natural numbers or whole numbers are not a subset of T. If A is not a subset of B, then we write symbolically A, that is subset strike of not a subset of B. Please note down. If every element of B is also in A, then both A and B are same. So set A is a subset of B and set B is a subset of A. That implies A is equal to B. So this both side arrows is implies. Every set A is a subset of A itself. These are the properties of subsets. That is, A is a subset of A itself. Since the empty set phi has no elements, then phi is a subset of every set. So phi can be added because it has no elements. It can be added to every set. Phi can be a subset of every set. Proper subset. Let A and B be two sets. If A is a subset of B and A is not equal to B, then A is called proper subset. Hence, there are two conditions for proper subset. That first condition is A should be a subset of B and A should not be equal to B. Then A is called proper. Otherwise, it is called improper subset. Singleton set. If a set has only one element, we call it a singleton set. Example A. Within bracket A, only one element is there, A. So it is called single element. Sometimes we write it also as a phi. Intervals as subsets of R, that is real numbers. Let A, comma B, then set of real numbers y such that y is A is less than y less than b is called an open interval, and this open interval is denoted by within small brackets a comma b. Please note here a comma b within small bracket, and this is open interval. But A and B, comma, themselves do not belong to this interval. So this is not including A and B. The interval which contains the endpoints is called closed interval. And the closed interval is denoted by big brackets or a square bracket. That is, open square bracket A, comma, B, then close the square bracket. Thus, A comma B within square bracket equals x such that A is less than or equal to x, less than or equal to B. So please note here less than or equal to. Hence it includes A as well as B. This closed interval is represented, is shown in the diagram. You see here A, point A and point B. So the in between these two is shown in the blue color, and this is written as within square bracket A comma B. So this is a closed interval because, and you can see here A is less than B, that is B is greater than A. So it is written within square bracket. This is a closed interval. If it has got a square bracket, it is a closed interval. We can also have intervals closed at one end and open at the other. So here you see in the second figure, A is a closed interval. It is a black. So it is a square bracket A comma B closed with small bracket. So B is an open interval. The end B is an open interval and A is at the closed interval. Hence, square bracket a comma b is equal to x such that a is less than or equal to x less than or equal to b is an open interval from a to b, including a but excluding b. So, small bracket a comma b with big bracket equals x is such that a is less than x but less than or equal to b is an open interval from a to b but excluding a. So this is shown here in this diagram number 3. Another example, if a is equal to minus 3 comma 5 and b is equal to minus 7 comma 9, then a is a subset of b because b is from minus 7 to plus 9, whereas a is minus 3 comma 5, which fall within the closed interval minus 7 and 9. Hence, A is a subset of B. The set big bracket 0 comma infinity defines a set of non-integers. So, infinity, this is an open interval at the right side but closed interval at the left side. That is because it starts from 0. Hence, define the set of non-negative. 0 and towards this is positive numbers. All are positive numbers or non-negative numbers. Set minus infinity comma 0 defines the set of negative real numbers. Hence, we can also define a set minus infinity to plus infinity as within small brackets minus infinity comma infinity defined set of real numbers. Next, we will take up power set and universal set. Power set. The collection of all subsets of set A is called the power set of A and it is denoted by capital P within small brackets capital A. In P of A, every element is a set. Here you see every element within brackets is a set, not a number. It is a set by itself. Hence, it is a power set. Example, if A is equal to 1 comma 2, then power of A is written as, here we are adding 1 5, that is singleton set 5 comma within flower brackets 1 comma 2 and 1 comma 2. So this is a power set. Also note that number of P of A within big bracket equals, here you see 4. There are 4 elements 5, 1, 2, 1 comma 2. There are 4 elements. Hence P of A, n of P of A is equal to 4 is equal to 2 square. In general, n of A is equal to m. If n of A equals m, then it can be shown that n of P of A will be equal to 2 to the power of m. Please note it very carefully as there will be one mark question on this, on power of set. So this we will show when we take up multiple choice questions. Next is universal set. Generally, we deal with the elements and subsets of a basic set which is relevant to a particular context. For example, while studying the system of numbers, we are interested in the set of natural numbers and its subset such as the set of all prime numbers, set of even numbers, so forth. This basic set is called universal set, which is denoted by capital U. Please don't confuse with another symbol which you are going to study as union. Union is also similar to U, but it was a cup. This sign is resemblance. That sign is called cup, but this universal set is capital U, and all its subset by letters A, B, C, etc. Venn diagram. The relationship between sets can be represented by means of diagrams which are known as Venn diagram. The universal set is usually represented by a rectangle and its subsets by circles. The elements are written in circle. These Venn diagrams, universal set, etc., we will take up in detail when we study operations on sets. That will be in our next session. Thank you.